Well, this is Mike Vella, and I'd like to welcome you back to our practical problem-solving clinic, where we've been discussing experimentation techniques. This is part 5 of the 5-part series. Part 5 details how to perform a Taguchi designed experiment without full assignment in the columns. Our example will have 5 of the 7 columns filled. That'll leave us with understanding how to deal with the primary error that exists in the 2 empty columns. So here is the premise, the cutter problem. You work for a company that manufactures residential air conditioning units. You know, those units that sit outside your house with a big fan running in the summertime. Thin wall aluminum tubing is a major component of the air conditioning's heat transfer technology. As the plant's quality engineer, you've been informed that tubing length control has emerged as one of the plant's major quality problems. The quality team has narrowed the problem down to a single high-volume tubing cutter. As a result of the poor quality cuts, your quality technicians have placed several lots of work in process cut-to-length tubing on hold. The operations manager has ordered the cutting line shut down until the problem has been identified and resolved. In addition to the loss of capacity, this issue has resulted in excessive scrap and is threatening to impact on-time delivery, which is driving overtime costs on other cutters. Your boss, the quality manager, has assigned you to be the team leader. You have formed a problem-solving team to address and resolve this problem before it really gets out of hand. Here is a typical small diameter tubing uncoiled cut and straighten line. I took this picture off the web from the Wilton Machine Company. If you're interested, you can visit them at that site. How this works is you start with coiled tubing, and you can see there's 2 coils back there. The machine's running off the coil to the left, and in order to have a continuous process, there's a splicing operation. When that first coil is completed, the turnstile rotates, and then the second coil is spliced on so you can have a continuous process. The tubing then advances or is pulled by what is inside that first yellow box. Those will be typically the pulling rolls, or they might be considered pushing rolls. And then it goes through a straightening operation and a cutting operation, which is found in that second yellow box. The tubes then are formed into cut lengths, and they are straightened and they roll down that trough to be entered into the next process. So as you recall, there are 8 steps of conducting a Taguchi experiment. We'll go through all 8. First and most important is planning the experiment. Second, selecting the appropriate orthogonal array. Step 3, selecting a linear graph that allows best assignment of the factors to the orthogonal array. Very important if you suspect that you have interactions. Step 4 is assigning the factors to the column of the array so that you can run an efficient experiment. Step 5 is to run the experiment. Step 6 is to analyze the experiment. Step 7 is to draw the appropriate conclusions from the analysis and optimize the factors. And step 8 is to verify the result by performing a confirming run. Your problem-solving team has brainstormed the potential causes of the problem and have determined that 5 process variables, those are factors, have the greatest impact on the cutter's length control. That's feed roll material, feed speed, die clamp pressure, feed roll pressure, and stop spring pressure. The team reported that all of these variables have been modified over the last few weeks in attempts to resolve the problem. You've concluded that the trial and error system of experimental design has not worked out as expected. Some of the changes were based on operators' opinions of what they thought ran well, while other changes were made under the control of the maintenance team. Unfortunately, your roll materials have been changed due to your problem with your supplier's inability to deliver a consistent product. The team agrees to run an experiment as a 2-level design. So for the 5 variables or 5 factors, the current column illustrates what we're running now, and in the new column is what they are proposing to run. So roll material goes from hard to soft, feed speed goes from fast to slow, clamp pressure from low to high, roll pressure from low to high, and stop spring pressure from low to high. As a note, in planning designed experiments, choose experimental levels in such a way that they will mirror what will happen in real life. You don't want to select factors that are out of the world or never could be conceived or you don't think would ever be supported by the machine or the operation. And at the same time, the levels should be different enough so that they span the entire range of possibilities. You don't want to make a very small change in a designed experiment. After all, what you're trying to find out is if that factor makes a difference. The output variable in this case is tube cut length. An inside micrometer is used to set up the production length gauge to the cut length, and a gauge R&R study shows an acceptable degree of precision. Now, how this normally is done on a very long tube is a setup bar is placed in the gauge. Think of it as a very long ruler with a precision stop, and that bar is a precision end. Let's just say it's 5 feet, and let's just say our cut length is 5 feet 6 inches. Those 6 inches would be made up with this inside micrometer where you have 2 precision ends and a barrel that acts as a micrometer, and you dial that last few inches in and lock in the gauge. The target length is set to 0 and data is reported in increments of 1/1000th of an inch plus or minus from the target. Noise or unexplained variation will be controlled. That means we're going to try to limit it by running the experiment on a single batch of raw material tubing with all other machine-related factors remaining as constant as possible during the test. So in terms of measurement error, recall that measurement error is a source of variation in the data set. In analysis of variance table and ANOVA table, measurement error is, unfortunately, it's mixed in with the residual or experimental error. If the measurement error is high, it will hide and confuse us, and the effects of the variables will lead, this whole test will lead to false conclusions. So it's very important that before you start the experiment, you have to confirm that your gauging system is very good, and that includes running a repeatability and reproducibility study, which includes different operators, different parts, and over different times, so that you know that your gauging system is reliable. The team decides that they will use a Taguchi design with 3 repetitions of each trial. While this is good, it's not absolutely ideal, but the team understands that the urgent need for this cutter to start up and run good quality cuts is very high. The team chooses repetition strategy over a complete randomization with replications of each setup. So the experiment will be run by an experienced cutter operator under the supervision of the engineering department. That's very important, so there's a good observation of anything that may enter the experiment. We want to take note of it. The factors for each trial have been agreed upon by the team, and a senior quality technician will collect the samples and perform the measurements. As team leader, you will supervise the analysis and issue a report. Again, the teams brainstorm 5 factors, each to be run at 2 levels. The team decides that interactions are not likely for this experiment and agrees to only look at the main effects. And a Taguchi L8 is chosen as the appropriate orthogonal array. The L8 has the ability to evaluate as many as 7 factors in 8 trials. Typically, linear graphs are designed to track interaction between experimental factors. The team has determined that interaction of factors are not likely in this case, and therefore consideration of linear graphs is not necessary. You can see a linear graph on the right. As a note, for an L8, there are 2 linear graphs. The one you see on the right is one of the 2. So here is our L8, and we want to remind ourselves that to take advantage of some strategies that makes the Taguchi an efficient run test. So what you'll want to do is those factors that are very difficult to change or expensive to change or time consuming to change, you want to change them less. So those factors should be preferentially put into column 1 and column 3. You can see that in column 1, the factors only change once. You can see that between experiment 4 and 5, whereas in column 3, it changes twice, 1 to 2, then 2 to 1. In all the rest of them, they change more than that. So when you're assigning factors, be mindful of where you put them in the column array. So the team has decided to assign these different factors with their designations to the columns, as you can see. So stop spring pressure was assigned to column 1 because apparently it's most difficult variable to change. The stop spring pressure. That's the trigger, so when the end of the tube strikes the stop spring, it electronically triggers the cutter to cut and advance the next product. So here is our table now with the different factors assigned across the top, E to 1, D to 2, and so forth. And primary error is going to be addressed in columns 3 and 6. Those are the 2 open columns, if you will, in the 7-column design. Remember, we only have 5 factors. On the right, we're going to be collecting 3 samples from each run, and we're going to record the data in the table. While it sounds a little bit too tedious, it's important for you to create a table like this because you're going to be giving this to the production people, to folks who are not necessarily very familiar with this process, and you want them to understand that how to run the trial. For example, in trial 1, we're going to run all the factors at the low level, 1, 1, 1, 1, 1, all 5 factors. In number 2, E and D are going to be run at 1, C is going to be run at 2, B is going to be run at 2, and A is going to be run at 2. And where I've seen folks have problems is they're given a list maybe written out and they don't seem to be able to follow the assignment. Using a table like this, they can be reminded what factors have to be changed during what iteration in the experiment. So let's take a moment to discuss some of the terminology we're going to be seeing eventually in all the tables coming up. And we're going to do that by what we call separating the variation. First off, we're going to be talking about main effects. And the main effects are what accounts for the variation when we change from level 1 to level 2 in this 2-level experiment. So when we change in factor A level 1 to level 2, that's a main effect, and we're going to account for that. SE1 is primary error, and that accounts for the variation in our empty columns. In this case, we have a 7-column experiment, we have 2 empty columns, and so we need to account for that variability. SE1 accounts for that, and the calculations for it is similar to how we account for the main effects. The sum of main effects and primary error equals what we call ST1, or the primary sum of squares, and that accounts for the variation between the averages of the total runs. Also, as I mentioned, is the sum of the main effects and primary error. We don't use ST1 in terms of any F calculations. It's used just to check our arithmetical work. SE2 is secondary error. That accounts for the variation within each trial. Remember, this whole business is just like we see in our X bar and R charts. We're calculating the difference between within and between variation. So SE2 accounts for the variation within each trial. It provides an estimate based on the variation between individuals within a cell between consecutive parts. That's SE2, or secondary error. And it all total up to what we call ST2, or the secondary sum of squares, accounts for the variation of the individual measurements and also is the numerical sum of all other errors. So as I mentioned, ST1 and ST2 don't factor, if you will, in the creation of the table, other than to help us with the numerical summing and doing a check on the arithmetic. Running the experiment. Although we know that it's better to randomize the order of the trials, in practice, noise or unexplained variation is often controlled more by attempting to control all the variables not included in the experiment. So, for an example, in this particular cutter example, there may be some lubricant that's applied to the cutting mechanism. You want to make sure that that lubricant is running all the time and the oil is clean, that there's some not some anomaly that's creeping into it, or that there wasn't some kind of power surge in the plant, or that the air compressor normally running at 100 psi somehow drifted down to 60 psi. You want to make sure that some crazy factors that could happen during production are accounted for. And if it does happen, it's fine. You just rerun the experiment. You just don't end up with some really funky numbers. Remember, the team agreed to take 3 samples for each trial, and you've advised your quality technician to develop a special table or form for data collection, and they did a nice job with that. So here is our completed table. I've included the variable designations in the upper right-hand quadrant, A through A, B, C, D, E, and what column they were in, and you can see the results in the data columns. Remember, these are reported in thousandths of an inch, so that's 11 thousandths from target in row 1, item number 1, 17 thousandths, 14 thousandths, so forth. And of course, all the way to the right is the numerical sum of the 3 data points in each row. Well, to help with calculations, as we've done before, it's a good practice to create something we call a supplementary table, which includes totals for each variable at each level. For example, we began by summing the data for all the items drawn while A, the roll material, was at its first level. Then we repeat this task for the data that occurred while A was at its second level. Remember, A is assigned to column 7. So A is at level 1 for trial. So if you take a look at A, so that would be in column 7, and then you come across the rows, you're going to pick off the data that is associated with A at level 1. So that's 42 plus minus 5 plus 36 plus minus 20. And the same thing then for A at level 2. So then we create our supplementary table with that information, and you do the same thing with factors B, C, D, and E. And then eventually we'd do it for the empty columns, columns 3 and 6 as well. And what results in our supplementary table is a summary of that data. So in column 1, 2, 3, 4, 5, 6, 7, and total at level 1, total at level 2, and of course, they should all sum to be the same number, 93 in this case. Well, in this step of the process, you may want to just stop and sort of hold a pause and take a look at your supplementary table and consider the main effects contrasts. What I mean by that is, for example, if you take a look at your supplementary table and just in raw terms, look at the difference between a factor E at level 1 and factor E at level 2, and the difference there is 37. Factor D, 199. That's a big difference. Compare that to factor C, B, and A. Those differences are very small. And the whole point of this exercise is that we don't know which factors are the most impactful on the process. And if you did nothing else in your calculations, you might just stop right here and just say, you know, we got a sort of good look at this. We have 5 factors. A, B, and C are really no big shakes. We better concentrate on D and E. And of those two, D looks like it is most significant. And you might be very happy just to stop there and run another trial. So the whole point of the Taguchi approach is that this is an engineering approach, not necessarily a mathematical approach. And the idea is to test and retest and continue to test and probe your process until you really get the truth out. And by running these tests quickly with low cost, you're able to benefit yourself. Now we're going to go through all the calculations so that we can, show you how it's done. But many times I've stopped at this point and just said, hey, just a quick and dirty trial. These two fall out as big deals. The rest of them not so much. Let's stop and go on. The first thing we'd like to do is get a handle on the sum of squares of the main effects. In this case, we're going to be calculating the main effect for factor A. That would be in column 7 all the way to the right. So the total of those elements in total level 1 are 53. I'm going to subtract 40 from that, square that, divided by 24, because that was the total number of individuals in the experiment. And if you do that math, the sum of squares A is 7. Now later on, again, we're going to be talking about degrees of freedom, and degrees of freedom is 1 less than the number of values that went into calculating it. But so far, in this particular case, we're going to be talking about the sum of squares main effects, in this case for level A, for factor A. And we do the same thing for factor B, C, D, and E. And they'll go into our Taguchi table here in a few minutes. Now we're going to account for the primary error that's in column 3 and in column 6. Of course, we didn't really test anything, but this is the error that's going to be captured in the experiment, and we do that by examining the contrasts. 42 minus 51 squared. You can follow that in column 3, 42 minus 51 plus what's found in column 6, 49 minus 44. Square that, divide that again by 24, and you'll find that the primary error is 4.4. The next thing we're going to be doing is, as we mentioned in the previous video, we're going to be using this Taguchi designed or suggested shortcut called the correction factor. And this will help us in later calculations. And correction factor is the sum of the individual measurements squared divided by the total number of measurements. So the sum of the individual measurements squared, that's 93 squared, divided by 24, which is the number of individual measurements. So the correction factor is 360.4. Next, we're going to be calculating the total sum of squares, the ST2, and that is the sum of each individual squared. Add those up and subtract the correction factor from that. So if you take each of the individuals data points, 11 squared plus 17 squared plus 14 squared and so forth, add those every one of those squared and subtract the correction factor from it, you'll find the number is 2189 minus the correction factor of 360.4, and therefore the ST2, the total sum of squares, is 1828. It, of course, again, with one number less than the total number of items that went into making it, has a degree of freedom of 23. ST1 is the primary sum of squares, and it's calculated by examining, if you will, the total column all the way to the right. So 42 squared plus 38 squared plus minus 10 squared. Add those up, subtract the correction factor again, divided by 3, and you'll find that number is 1723.9. Again, degrees of freedom will be one fewer than the number that created it. So the values of all the sum of squares calculated to this point can be checked by the following relationship. Again, the ST2 and the ST1, those are really just sort of check numbers. Make sure we've done the math correctly. So ST1, or the primary sum of squares, is ST1 equals all the main effects, SA, SB, SC, plus the primary error. And that's 1723.8. Because we've taken 3 samples per trial instead of just 1, we can also estimate error within a given cell, called a secondary error, by using this formula. Secondary error equals the total sum of squares minus the primary sum of squares, which is, from our previous calculations, 1828.6 minus 1723.8, which is 104.8. So with all that arithmetic, we're ready now to construct our ANOVA table. On the left-hand column, we have all the sources, A, B, C, D, E, and the 2 error numbers with the degrees of freedom that are associated with it, the sum of squares that we calculated for each, and then, of course, the variance is the sum of squares divided by the degrees of freedom. So for factor A, the variance is 7. That's 7 divided by 1. So the whole calculation here with the ANOVA table, and this is, as we mentioned some time ago in our presentation, this is an analysis of variances to determine if means have changed. And we're assuming that the data has been collected from a distribution of individuals that is from a normal distribution. And the idea is that if that is the case, then the ratio of variances will create something called the F distribution. And we want to compare our variances from this F distribution to see if it falls within that F distribution, which would mean that we would accept the null hypothesis that nothing has changed, or reject the null hypothesis and say something actually has changed. And we make that statement that something has changed. We say that it's significant to some degree of error. Either in our case, we talk about either a 5% chance of making a mistake or a 1% chance of making a mistake. Now, we have discussed in the past this issue of pooling. Some of the variables that we've noted, for example, factor A and factor B, factor C, and the error factors E1 and E2, well, their variances are so much smaller than the other variances. Compare that to the variance of factor D, which is 1650, and factor E, which is 15.7, that we collect those variances and we pool them, together. And when we pool them, we put that little dot on the right-hand side. And so when we make this calculation, and I'll read the instructions on the right-hand side. Since we have two estimates of experimental error, E1 and E2, we must decide which to use. The general rule is to use the test ratio E1 over E2 to see if it exceeds the critical F value for alpha at 5%. If it's not significant, we'll combine the two and form a pooled error, which we call E. So if we go to the bottom, E1 divided by E2, that's 2.2. You find that in row E1, divided by E2, which is 6.5. And so that ratio is 0.34. With degrees of freedom in the variance E1 is 2. The degrees of freedom in variance E2 is 16. So you look in the F table for 5% with degrees of freedom 2 and 16, and you find the critical value is 3.63. But since 0.34 is well within that critical level, we say it's not significant and we can pool those errors. So now we have a more complete table where we have pooled the variances and our error terms. And so now you'll see a new line that says E for combined or pooled error, and that's 5.79. And what we're going to do now is we're going to be contrasting or creating a ratio of D over E, and in fact, which is 1650 divided by the 5.79, and E, the 57, divided by 5.79, and then determining if those indeed are significant. Just one more word about pooling. There are two guidelines about pooling. First guideline, rules of thumb, is that factors that have a F value of less than 2 are candidates for pooling. If an F value is less than 1, it certainly should be pooled. If all the columns are used and there is no error term to use, then pool until about half the degrees of freedom are included in the ultimate error term. So here is our new table with pooled error that we've calculated. And the next step for us is to discuss the F value. So now we're finally ready to make a decision about significance. And since we've pooled factors A, B, and C into the experimental error, that means that they were not important in terms of the range of changes that we made. Only factors D and E remain to be tested. We calculate the F by taking the following ratios, and that is the 285 is the ratio of the variance of factor D, which is 1650, divided by the variance of E, which is 5.79. So that's an F value, 285. And the variance of factor E, which is 57, divided by 5.79 is 9.8. So then when we go to our F table, which I introduced to you in the previous video, section 4, you check our F table and we see that the F, or the critical F value for a 5% error with degrees of freedom 1 and degrees of freedom 21, that's 1 degrees of freedom, see the left-hand column, and 21 for the factors in the left-hand column for the error term 21. The critical factor is 4.32, and you can see that 285 and 9.8 are greater than 4.32. Well, since both calculated F values, 285 for factor D and 9.8 for factor E, are greater than the critical factor, 4.32, we conclude that changing these factors, D and E, indeed did have an effect on the process. A statistician would say that these factors are significant. In Taguchi DOEs, we mark them with an asterisk. The asterisk signifies that there's less than a 5% chance of us mistakenly drawing this conclusion that the factor produced an effect. Well, since we have our statistics book open and we've looked at the F table for 5%, what the heck, why don't we take a look at the F table for 1%, degrees of freedom 1 and 21, and we find that that critical number is 8.02. And since 285 for factor D and 9.8 for factor E are still greater than 8.02, we can also say that there's less than a 1% chance of us making a mistake when we call these two factors, roll pressure and stop spring pressure, as significant. These are highly significant, and we put a double asterisk behind the F. So oftentimes in presentations, it's helpful to graph the main effects as a visual aid to present your results. We calculate the average of each value in the first at level 1, and then at level 2, and plot them as a straight line. This task is made easier by using our supplementary table, which shows the sum of the individual at each level. The averages are calculated, of course, by dividing the sum by 12. That's 4 trials times 3 repetitions. And you can see the little table on the bottom, which then can create the main effects graphs if you choose to plot them. Here's an example of the main effects for factor A. So the next thing we'll want to do is verify the results. Since D&E produces an effect, since only D&E produced an effect on the process, we verify the results by setting these factors at a level that produce the best value, best length control value, and sample the process. Of course, the best value for length control is the smallest one, the one close to 0. So what we want to do is set both factors at level 2, D at 2 and E at 2, because they're closer to 0 than D and E at level 1, and then resample the process. Now, in a confirming trial, you may want to anticipate or predict what you think the results will be. And to do that, you can create this little calculation, which means, so the mu, the estimate of mu, the estimate of what we think that the process average will be in long term, is the average factor D2 plus the average factor E2 minus the total. So it's minus 53 divided by 12, which has become an average 28 divided by 12 minus the 93, the total divided by 24. And so we think that if we set the factors at those levels, on average, our cut length is going to be minus 5.9. And if we want to get to closer to 0, then now it's just a matter of setting the bump stop in a way so that the numbers will come closer to 0. So with all this great work and effort, you would expect that the confirming run will verify the results of the experiment. And very significantly, you have achieved at least 2 positive results. First, you have determined which variables control length variation and can plan accordingly. Concentrate on these variables and, to a great degree, ignore the others. You have improved the process by adjusting to the best levels and concentrating your production organization to watch those two factors and not so much talk about the others. Since the other factors are not statistically significant to tube length control within the range of these settings, they can be set anywhere you like. This decision should be made based on cost. For example, if speed does not influence length control, run at the maximum speed. So remember the Deming-Schuhart improving cycle, and that is the plan, do, check, act. You've planned an experiment, you've run it, you've checked the results and acted on the results. Now continue. Repeat, 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 repeat. This is what Taguchi really struck out to do with developing these orthogonal arrays. He wanted to create an environment where people in their engineering teams can continue to test and perfect their products using quick and easy to use experiments, and to continue to perfect and hone the products until they got them as perfect as they could. And they couldn't do that using the full factorial experiments that we talked about previously, or the more laborsome and mathematically pure fractional factorials that Dr. Fisher introduced. So I want to congratulate you on making it through this introduction of hypothesis testing and designed experiments. There are a lot of good references that are available with other designs. Don't be intimidated. Thank you very much. But again, credit to the Greater Detroit section of the American Society for Quality Control for their introduction of hypothesis testing for me. First time I came across this methodology was in 1978. And then in the early 80s to the Ford Motor Company and their work with the American Supplier Institute. And they're leaning on Genichi Taguchi and Yuan Wu and their work documenting Taguchi designed experiments in a book called Offline Quality Control. And for my great friend and colleague Tom Dold for his enduring work in training and continuous improvement. Thank you.